Hi guys, welcome to the video on volume. And today we're going to talk about volume of different shapes. And remember, volume is kind of an example of how much stuff fits inside, how much space there is inside of a 3D shape. So questions like volume deal with what's the, how much water could you fit a pool, or could fit inside of a pool? Or, for example, let me show you. Example that all of you seem to be, or a lot of you seem to be using Rubik's Cubes lately. So the question for this, using this Rubik's Cube, would be, what's the volume and surface area of this cube? So think about that for a second. If each of these faces represents one, we'll say, unit. It's definitely not an inch, it's smaller than that. But if this is 1 unit by 1 unit, this is the red dot up here would be 1 square unit. Alright. So my question is, obviously one of these cubes, this first right-hand cube here, this cube would be a volume of 1, because 1 times 1 times 1 is 1. So what's the volume and surface area of each of these, of this whole cube? All right. So for surface area, we could start by saying, well, how many actual stickers would you need to cover this whole thing? So since it's a cube, if we find that we can find one side and then multiply it by how many sides are on a cube, which is 6. So if we just look at this white side first here, or the white dots here first, the surface area of one side would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So the surface area of this would be 9, but then there's 6 sides, so 9 times 6 is 54. So there's 54 colored dots over this whole thing. Makes sense. Now, for the volume, you'd have to figure out, basically, how many cubes are inside this whole entire thing, including what's inside the middle, what you can't see. Now, I know a lot of you have started to take these things apart and snap off different pieces, and you probably know that there actually aren't cubes in the middle. But if there were cubes in the middle, how can we figure out what the volume of this is? A lot of you will probably figure out that you can multiply length, width, and height. But we're going to do a different formula today, one that applies not to just cubes, but other figures as well. All right, so that's the most important thing. So if we notice that this cube here is 3 by 3, that'll help us here. So here is, if you imagine in my 1 inch by 1 inch blocks, here is a big Rubik's Cube. All right, so I have all the different sides that we need here. Notice it's still 3 by 3. So we need to figure out the volume of this entire cube. The surface area would still be 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 6 is 54. So the surface area is 54, we'll say inches squared for this case. All right, 54 inches squared for this case. But we need to figure out what's the volume. What's the amount of space that's inside here. So let's take this apart layer by layer. And there's a couple ways we can do it. First way. What if I remove this, so you can kind of see that part? Take this over, and then this one over a little bit more. And kind of rotate them so you can see. Could you now count up how many cubes there are? You should see that there are 9 here, and 9 here. So 9 plus 9 plus 9. If we actually add those up, 9 plus 9 plus 9 gives us, 27. So the volume is going to be 27 cubes. And we're going to figure out a formula for a way to do that today. Now if I put them back this way, I could also take them apart another way. I could cut them apart this way and make different stacks. Okay, so now you can actually see, if I go this way, that there are 3 groups of 9. Alright. But basically the way we're going to talk about it today is we're going to talk about the area of the base of this. Okay, the base of this, which is 9 blocks, fit in there. But then we're going to multiply it by how many layers there are. So there are 1 layer there, 2 layers there, 3 layers. Okay, so this is actually 9 times 3 layers. So 27. I could add more and more layers. We could do different types of shapes, but let's kind of talk about a couple different examples with not just cubes, but of different types of figures. So, if you get your notes out, we'll take a look at a couple of these. So the first shape we're going to look at is a rectangular prism. If you imagine the way that we kind of sliced this apart before, you know, this is 8 here, so it would be, that won't work out too well, but 8 different units here, 6 high, and 13 across. Now to help you with this, it's definitely going to be helpful to think about all the different ways that, or all the different places we could put 6 meters. So this 6 meters is also a couple different places, and I didn't write it in there for you, but you need to figure out where it also goes. So since 6 meters is the height of the 3D shape, 6 meters could go there, there, or there. So all of those could be 6 meters. You don't need to write this in, actually, because we're going to do a couple other things with this shape too. But just kind of watch here. 8 meters is this distance here, but 8 meters also goes somewhere else. It goes on the other side of my rectangle, but also directly above it, up here and up here. So the 8 meters is also 4 different places. And obviously you can probably see the last part here, the 13 meters is the length of this line, but it's also the length of the other horizontal lines. So just because you're given one measurement, you have to be able to figure out all the other places that it could be. So the formula for volume of any prism or cylinder is V equals capital B times H. Or in words, that capital B stands for area of the base times the height. Okay. It stands for area of, you know, those 3 blocks that I had on the bottom. And then that's just the bottom layer. And now Rubik's Cubes has, you know, more layers, 2 more layers after that. So the first thing we're going to do is figure out which shape is the base. We're going to outline that base and then, you know, kind of signify what the height is, and then do our formula. So in this rectangular prism, we know that we can actually use any rectangle as the base because they're all rectangles. All the opposite sides are congruent here, so it doesn't matter which rectangle we use. A lot of us like to use the bottom one just to make it easy, which is fine. So the first step I want you to do is actually, in another color, a pen, a highlighter, whatever you have, outline the base. And I'm going to say that the base we're going to be using is 8 by 13. So this base is going to be 8 by 13. We're going to find the area of the base, which is capital B, and then the 3D height. I also want you to outline the height in a different way, just kind of maybe like a squiggly line or something like that, so you know which one is the height. And the height is the distance from the top base to the bottom base. So it's from that bottom rectangle, the green one, all the way up to the top rectangle that's not highlighted right now. So our 3D height is 6 meters. And again, the height's not always just up and down. If we rotate this figure around, 90 degrees or 180 degrees, the height is not just going up and down all the time. So when we figure this out, 8 times 13 is 104. And then we have 6 layers of this. So we have B, we have H, we can plug them into our formula. Capital B is 104, and the 3D height is 6. When we do 104 times 6, we get 624 meters. And this is talking about how many cubes fit inside here. So we're actually talking about cubic meters. 624 cubic meters. So that's the example there. Now we could do this a different way. Just so you can kind of see the other way to do this, you can actually, erase this whole picture. You don't have to do this, but you could actually do this with the right side being the base. If the right side is the base, what does that make the height? So if we have those two base, or the base there, the other base would be the opposite side. The height would be this distance right here. That didn't work out too well. The height would be the distance from the two bases. So here the height would be 13 if we changed it around. You'll still get the same answer both ways. Just to show you another way you can do it, instead of the bottom being the base or the right side being the base, you could use the front and the back being the bases. So you could actually say that this front side is the base, and the back side would be the other base. And hopefully now you can see that the three-dimensional height would be, how do we connect those two? So it would be from here to there. So there the height could be 8. Now this is only for rectangular prisms. Other shapes it doesn't quite work that way. So the rectangular prisms, you have some kind of freedom in what you want to do. In your triangular prisms, the triangles are the bases. So while we're still using the same formula, B equals capital B times H, we're going to be using the area formula for a triangle, because the first step we're going to do is outline our base here. Here the base is not just the bottom part. The base is the triangle. So it looks like it's sitting on a rectangle, but we have to use the triangle as our base. So if the triangle, 5 by 12 triangle, is our base, our 3D height would connect the two triangles. So this 20 is the 3D height. Now to make things even more complicated, we also have another height. This height of our triangle. That's the height of our base. So there's two different heights, 5 and 20. This height is your three-dimensional height. It means from triangle to triangle. It'd be good to write that down. From triangle to triangle. From base to base. But the 5 height is going to be in our area of the base formula, the triangle formula. So anyway, let's keep going with this. To find capital B, that's the area of the triangle. We'll do 1/2 times base times height. And that's a little b there. So the area of my green triangle is 1/2 times 12 times 5. So when we do that, we get 30 is the area of our base. And then the h, remember this h up here is our three-dimensional height, which is from front triangle to back triangle, which in your head you should be thinking 20 there. So to plug everything into our formula, we do b times h. Our area of the base was 30, and our 3D height was 20. So when we do 30 times 20, we get 600, and that's our volume, inches cubed. There's the total volume. And the last shape, we have a cylinder now. Still the same formula. That's what's nice about these. Any prism or cylinder, capital B times H works. But in this one, our capital B is now going to be a circle. So for capital B this time, capital B takes many different forms. Now it's a circle. It's pi r squared. So here our radius is 1/2 of 20, which is 10. So it's going to be pi times 10 squared. And that ends up being 314.2. So capital B times H. Our three-dimensional height. Oh, I forgot to have you outline your height there. Go ahead and say your height is a distance from base to base. Our 3D height is 32. So for capital B times H, we're going to do 314.2 times 32. And that final answer is a pretty big number because we have pretty big dimensions here. It's 10,054, sorry I couldn't read my decimals there. 10,054.4, once again, inches cubed. So that's the volume. Once again, our big formula is capital B times H. But in the first example, capital B, we just did base times height. In our second example, for capital B, we did 1/2 base times height. In our third formula for capital B, we did pi r squared. So it depends on what shape your base is. Thanks for listening, guys. We will see you tomorrow.